Hello, everyone. Thank you for attending today's webinar titled Industrial Ovens, the Final Frontier, brought to you by Products Finishing and presented by Therma-Tron-X. I'm your moderator, Scott Francis, editor of Products Finishing. Today's presentation will last approximately 30 minutes, followed by a question and answer session. If you have a question, you can type it at any time during the webinar in the Q&A section of the chat. There's also a couple of handouts, so check those out. The webinar is being recorded and when complete will be made available to you via email from Products Finishing. Our presenter today is Brian Rozdilsky, a sales engineer at TTX. He has 20 years experience in the finishing systems industry and earned a degree in manufacturing engineering from Bradley University and his MBA from Roosevelt University. Brian, welcome, and I'll hand it over to you.
Well, thank you very much for the introduction, Scott, and I appreciate everybody joining us today for this presentation. Today, as the title implies, we'll be talking about industrial ovens, the final frontier. But before we get too far into the presentation, I did want to highlight that we do have a poll question off to the side. If it's sometime during the presentation, you could review that and answer the best you can. That way we can take your responses and try to improve future presentations and try to tailor that to your needs and requests. So for today, we're going to talk about various topics on the oven, highlighting curing ovens, but we will touch on dry-off ovens also. Starting with the purpose of the ovens, the requirements, initial sizing of burners and fans, different orientations, and heating elements for the ovens, and following up with maintenance, and then finally troubleshooting. Now, purpose of the oven, it's pretty straightforward. The oven is designed to heat a product to a certain temperature for a certain amount of time. And then again, as the title mentions, it is typically the final step in the painting process. So we really want to make sure we get the cure oven correct. If you cause defects in the oven, everything else that's happened prior to that has been a waste. You wasted manpower, resources, and energy. So it's very critical that we design the oven correctly. Just starting out with a simple layout on a finishing system, highlighting the two various ovens. There are other types, but we're going to focus mostly on dry-off ovens and cure ovens for this presentation. The dry-off oven obviously comes right after the pre-treatment system. Typically use high velocity, lower temperature air to not only blow the liquid off the product, but also evaporate the water from the product prior to the application equipment. After the application equipment, the powder, the liquid, the E-coat has been applied. It'll then travel into the cure oven where it will dwell for a certain amount of time at a certain set temperature to fully cure the part, or the paint on the part. When looking at a new oven, curing oven, dry-off oven, we want to make sure we clearly identify the requirements for that oven, for that paint. Are you looking at a Class A finish compared to just a general industry oven? There are different options that can be added to the oven to achieve the quality that you desire for your product. Also, what comes into effect is the type of coating technology. Is this going to be an E-coat, a liquid oven, a powder, or some other type of coating technology? That really drives the design of the oven in one direction or another. We're first going to start out talking about various oven configurations. First would be a batch style oven. This is the simplest and most economical to install, but it is designed around a lower production throughput. Parts are typically moved into a batch oven manually, either on carts or on occasion on a manual trolley. Parts are pulled in, the doors are closed, and the start button is pushed by the operator, and the cure cycle begins. Once the cure cycle is finished, either audible or visual alarm, you can see stack lights on top up here where it may alert the operator for an alarm or that the product is finished and can be removed. Another style of batch oven, which we refer to as a well oven, in this situation in the bottom left-hand corner of the slide, is using a hoist to drop or lower the part into a top entry oven. The carrier is actually an insulated panel roof that seals the top of that oven and keeps the heat from escaping. Batch ovens are very efficient, but they do require additional heat up every time you open the door or raise the roof off of that oven. When production requires higher production rates, a flow-through oven is typically used. Different conveying methods can be incorporated, such as a floor conveyor, as you see there, a power-free inverted floor conveyor, a monorail I-beam, an enclosed track, even something such as a mesh conveyor or rollers. The picture in the bottom center there you see is actually an indexing system where the parts index at a set cycle rate. So say every 3 minutes, these parts will move one station in the oven and fully through the oven and onto the cooling tunnel. And there's also a special combination when situations arise where you want to automate the parts being introduced or loaded into the oven. This picture shows an automated carrier moving parts into an oven where the doors automatically open. The carrier moves into the first station, doors automatically close, and then that part dwells in that first station for the cycle time. After that, it'll move into the subsequent cycle or stations for a full cure. Again, the combination and the batch are for lower line speeds or slower production requirements, and the flow through is for much higher. Now, how are we going to deliver heat to the product? There's a few different ways that we do that in the finishing industry. First, probably most widely used is the convection style. Very similar to possibly an oven you have at home. You're heating air, and that air is moving across the part and heating it thoroughly. There are quite a few advantages to a convection style oven. You can get a very uniform cure across the part. Complex geometries can be heated, and there's fewer hot and cold spots within the oven if the circulation ductwork is sized properly, and we'll discuss that a little further in the presentation. It's also a very simple system to operate. With a convection style oven, you have few moving parts, a few fans, a burner, and a gas train. So it's very easy to maintain. A second operation that can be used, a second process, is infrared or IR heating. IR heating uses various elements or heater beds to heat the product, sending it directly to the part. Instead of heating the air, the infrared heats the part directly. One downfall, it is line of sight. So if you have parts that have varying geometries, maybe cavities, the IR is going to have a difficult time heating those areas. Just a few examples of different types of infrared curing is a shortwave heater, typically heated through electric means and has a very high face temperature. The electric also has a very fast recovery or heat up and cool down. So if, for example, a product conveyor is stopped in front of the infrared emitter, that IR can turn off immediately, which reduces the possibility for overbaking or over-curing the product. The medium wavelength, which is most prominent in powder coating ovens, uses a slightly cooler face temperature and has a slightly longer heat up time, roughly 60 seconds. The long wave emitters aren't used too often and have a much longer heat up time of about 5 minutes. Since the infrared is a different technology than the convection, you have to be aware of, as you see in this image in the bottom right, that some of the energy may pass right through the part and not heat it up. Depending on your paint color, your substrate, you may even reflect some of the energy back off and not be absorbed. So you're looking for as much energy to be absorbed into the product. Whenever you're looking at using infrared, whether it's a booster or for a full cure, always test prior to purchasing or installing a new system. There are many companies out there that can do testing very easily for you, so you can prove out that process before you put all the work and capital into buying a system. At the end of the day, the oven is designed to cure a product at a certain time and temperature. Every paint comes with a cure window. That cure window gives a temperature on one axis and a time on another. So for example, if you're going to want to cure this part, you need to cure it at 356 degrees for 15 minutes. Or you can cure it much hotter and do it in 5 minutes. But keep in mind, this temperature here is not time in oven, it's metal temperature. So if you have a much thicker part connected to a thinner part, you may need to dwell in an oven longer to make sure all the parts of that component are up to temperature for that 15, 30 minutes, whatever the oven is designed for. So there are a few different heat sources that you can use for heating the oven. Most prominent is natural gas. It's very available, fairly inexpensive, and used widely throughout the industry. In certain areas of the country, natural gas is not available, so liquid propane is used. And the same is true for electricity. In most areas of the country, electricity is very expensive to power an oven. But in some areas, say down south, where they have hydroelectric dams, where electricity is much cheaper, this is a good option. Most oven comes with two different zones. For example, an E-coat oven would have a dehydration zone. As you see on the slide, roughly 212 degrees. You're looking at heating up the part slowly, evaporating the water from the E-coat paint. You don't want to hit it with too hot of paint and boil out the water, which would cause part defects or paint defects. Likewise, a powder oven has a gel zone, which you can use hotter temperature, but you must use lower velocity air so you don't dislodge the paint from the substrate. Moving into the cure zone, even the cure zone could be segregated into multiple temperature settings as long as you have independent heater boxes. But on average, E-coat and powder ovens run around 350 to 400 degrees, where a liquid oven could run cooler, somewhere around 275 to 300 degrees. After the parts are cured, they go into the cooling phase. This could be done a couple different ways. The most inexpensive is to just run the parts through the plant and let them release their heat into the facility. Adding heat to the plant, maybe in the north, that's not a bad idea in the winter, but it also could be a safety concern where operators may inadvertently touch hot parts and burn themselves. More often than not, cooling tunnels are supplied, which encase or enclose the part and conveyor and use forced air to cool the parts prior to exiting the cooling tunnel. On some occasion, misting nozzles will be used to cool heavy weldments that are very thick and take a long time to cool, in conjunction with chilled air units to help reduce the air temperature even further. So now we've learned a little bit about the ovens and how they work. We need to now design it. What does TTX or another system house need to know to design this oven? Well, first, line speed. How fast is your system moving? That'll base on how long the conveyor needs to be if it is a continuous system. Load size and weight obviously will size the burner. The heavier the product, the more BTU input you'll need to put into the oven. Oven configuration, where are we going to put this oven? On the floor, outside, elevated? And obviously that all comes down to heat loss, all the losses you're seeing from the panels. So here's a nice graphic of a Sankey diagram showing where the heat goes in an oven. So your gross input is coming from the burner. That's all the fuel you want to use, but right off the bat, you're losing exhaust losses. Out the stack, you're just BTUs flying out the stack. You want to minimize that. So you can put recovery systems on that exhaust to an air-to-air heat exchanger and recover some of that heat. You also have wall losses, constantly transmitting heat through the walls, opening, conveyor losses. If you have the conveyor inside the oven, you have to heat up the chain, the trolleys, and the rail. And at the end of the day, here's what you have left, the net output. So there are things that can be done to minimize some of these heat losses through an oven that I'll discuss. So first, starting with oven design, where are we going to install the oven? The most economical way to do it from a capital standpoint is to install it on the floor, on the factory floor. Your maintenance crew will like it because it's much easier to get inside the oven for cleaning, for inspecting, repairing, but you do have a lot of loss out the openings from the heat escaping. There are some things you can do to minimize that, but no matter what you do, you're going to have heat coming out those openings. To try to eliminate most of that heat escaping, you can elevate the oven to a bottom entry design. So the parts are actually entering the oven from the bottom, which means you have to increase the height of the oven on steel support columns and beams. It also opens up floor space for cooling, part storage, labs, whatever is required for your facility. Now, if, for example, you do not have any space available in your plant whatsoever, the oven can be moved outside. Here's two examples where you still have a floor-mounted oven, but it's outside the facility, and an elevated oven outside the facility with cooling below. This completely removes all the radiant heat that you would see from the panels outside the oven and saves floor space, but it is a little more costly. You have to install a concrete pad. You have to connect to the existing facility with flashing, and you can see on the top we actually flashed around the whole oven with decking. And then the most costly from a capital standpoint is a roof-mounted oven. This completely removes it from your plant, saves a lot of floor space, and is typically a bottom entry, bottom exit oven. So what are the various components that make up an oven? Starting with the insulated oven panels. These panels are aluminized or galvanized, skinned with mineral wool insulation in between. They can range anywhere from 2 to 4 to 6 inches, and it really is dependent on the temperature set point that the oven is going to operate at. You can see here, before I go to the next slide, that there are slots in the oven to help with oven expansion, so the oven panels don't push themselves apart when they expand, when the oven heats up and it contracts. The ovens are designed tongue and groove, so during installation they easily fit together, and all the corners are covered up with flashing, and all open areas are packed with additional mineral insulation to ensure there's no gaps or air leakages between the panels. Now, as I mentioned, on a floor-mounted oven, you have potentially large openings, which you're going to lose a considerable amount of heat. So air seals can be used to reduce the amount of heat. They're not going to be 100%, but they can be used to reduce some of the heat escaping the ovens. The first option is to use a gravity hood. So you'll install a vestibule previous to the oven starting. So this area is where the heat is escaping the oven and then travels up through the exhaust stack. It can be powered or unpowered. The next option is to use a powered air curtain. Again, roughly, depending on the size of the part, 4 to 5 foot vestibule prior to the start of the oven. And you're using a powered air to recirculate that air in that area, pushing the hot air back into the oven. And lastly, the most efficient is an elevated cure oven. These arrows are a little confusing. You shouldn't see any air coming into the oven from the bottom unless your oven is out of balance. If for some reason your exhaust fan is exhausting more than it should or not enough, you could be pulling air in or pushing air out of that bottom entry oven. Now, the heater units are the heart of the oven. This is where the recirculation fans, the burners, and the control panels are located. You can see there's a couple different orientations. The two pictures on the left and the bottom show an up blast where the fan is taking air from the top of the oven and then returning it to the bottom mounted ductwork. It could also be mounted on the top of the oven or the sides. It just depends on the configuration planned on and the space available in the plant. Now, the burner boxes, our heater units, are typically supplied with 2 control panels. There's one local burner box control panel in which are housed the flame relays, the flame safeties. These are the components that the maintenance crew are going to need to troubleshoot or work on the gas train, which you see to the right, and the burner. It makes it very easy for them to do that without having someone else stand at the main control panel or having to run back and forth to that control panel. Now, on the main HMI for the system, you can display much more information. If, for example, you have VFDs on the system, you can control or view the hertz that they're running at. Or even if you have the knowledge or the information in the control panel, you can see what the CFM of the fan is operating at. In addition to that, you can see the status of all the pressure switches, the fans, the burners. You can see the set point that the oven is set at. It's a good diagnostic tool. Even though there's a lot of alarms set into this, an operator can walk by the oven, see that the oven is set for 400 degrees, and maybe they see that burner 1 is at 350, and the valve, the gas valve, is 100% open. There's going to be an issue there. The burner is running full out, and it can't reach the temperature set point. So that's something to start investigating before it becomes a major issue. As I mentioned, every oven has an exhaust fan. So if you're exhausting air out, it needs to come back into the oven somewhere. So where we try to control the air to come back in is in the fresh air supply near the burner. This is going to introduce fresh, clean air into the burner for the combustion process and minimize the amount of air infiltrating through openings or through the bottom entry oven. Now, the ductwork is more of the arteries of the oven. This is what's delivering all the hot air to the oven. Ductwork design is very important, not to starve areas of the oven. Two different styles of ductwork is ceiling mounted, as seen on the left, which mounts all the ductwork up high, keeps the floor clean, reduces the amount of trip hazards, and makes maintenance very easy for sweeping out the ovens. Now, on the occasion you want floor-mounted ductwork for areas where you don't want high velocity blowing at the part, you can either discharge it very slowly through the top or even out the side and let heat do its job and rise slowly up on the part for, say, a gel zone in a powder cure oven. Properly designed ductwork should introduce air very similar to this diagram on the right. And as you'll see in this video, once the recirculation fan turns on, the rolling effect of the air in the oven, mixing very well, and imagine a part right in the middle of that area, swiping across the part and transferring heat very good across the complete size of the part. Another way to increase airflow in an oven, either initially or after the fact, is to add prop fans, roof-mounted prop fans to the oven. This can be done very easily when the temperature is not an issue. It's more of just moving more air in the oven in dead spots. So these can be placed throughout the oven in between conveyor sections. Now, the exhaust fans is an integral part of the oven to remove VOCs, to remove smoke, moisture. Here you see two exhaust fans. Per NFPA, you need to evacuate 4 turns of the oven before you can even ignite the burner. So typically we shoot for 20-minute purge time. Now, in a very large oven, that could be a very large exhaust fan, which would be running all the time. In this example, we have 2 fans. One is for running during production, and one is run as a purge fan. So both these fans will run at the same time to exhaust more air quickly. And then once the purge is complete, purge fan will turn off and the burner can be lit. Here's just another example of an exhaust fan located on top of an elevated oven. You can really put exhaust fans in many different locations on the oven. As I just mentioned, NFPA is the governing body for all the codes required for operating and designing an oven. So if you're new to paint finishing or you have old ovens, you may want to review the NFPA 86 code to make sure that you're still running in compliance, or if there's some things you need to do to get in compliance. So a VOC destruct system is used on an E-code oven, which when the paint cures, it releases VOCs into the atmosphere. These days, more and more people are becoming aware and concerned about VOCs being released. So this is a system that can be either added on the beginning or after the fact onto an E-code oven. It's quite simple, very similar to a heater box where air is pulled from the oven, which would otherwise be exhausted. It's passed through a media bed, which removes the fatty acids, VOCs, by the use of another burner, and then that cleaned air is introduced back into the oven. So by doing this, we reduce the amount of air that needs to be exhausted, which reduces the amount of overall BTU, increasing the efficiency of the oven. Now moving on to maintenance, whenever you have a system, a complete system, you should have a maintenance manual. And I can't stress it enough how important maintenance is in a finishing system, especially a cure oven. A dirty cure oven is going to make dirty parts. So sticking to a PM schedule is very important. Walking through the oven occasionally, seeing if you see any bent ductwork, any fallen parts, any dirt accumulating from conveyors. And filter maintenance. If you have filters in there, if you're not cleaning the filters, just like your home furnace filter, it's going to clog and you're going to start moving less air. You don't want your oven to end up looking like this. This is a major issue and obviously has not been cleaned in a long time. If they would have stayed on top of their maintenance and their cleaning, this would have never happened. It would have been much easier to do on a weekly or bi-weekly basis. So hopefully none of your ovens look like this. Now on to troubleshooting. There's a couple reoccurring issues that we quite often see in ovens, whether it be under curing, the ductwork is out of balance, the airflow is out of balance. You may see smoke coming out of the oven. So there's a couple different tools that I'd like to show you here that can help you. They're very inexpensive and easy to use. First of all, the FLIR camera. A couple $100 you can buy this camera, and this should be done as a benchmark. Preferably when you first install the system, walk around to all the motors and see their heat signature. This can be done on a monthly basis or every 4 times a year. Once you start seeing a motor overheating, that could be a potential issue. You might want to replace it or look at it a little further. Oven panels, something else that you can look at. Oven panels, like I mentioned, will give off heat. And in older ovens, it's a potential that the insulation can settle. So while you think the oven panels look great, they feel cool on the bottom, if you have a tall oven, they could be screaming hot on top because there's no insulation. It's all settled to the bottom. So again, getting a benchmark, seeing what those oven panels look like, and additional drives, all your components in the control panel, your VFDs, those will heat up. What are they supposed to look like and what do they look like today? Catch that problem before it shuts down your system. An out of balance oven happens all the time. Maybe somebody flipped a damper or a ductwork got closed, and now you can't maintain temperature. It worked yesterday, doesn't work today. What happened? So a simple tool that you can buy is an anemometer or velometer to measure the velocities of air either leaving or entering your oven. So for example, in this ground or level-based oven, you would take that anemometer and walk around at various points up high, in the middle, and down low and see what the velocities are coming out of that. Is it blowing in? Is it sucking out? That's a good indicator that something's out of balance that you need to look a little closer at. Even your exhaust fan. When you first started the system up, you should have received data telling you this exhaust fan is operating at this CFM. It may even be on the nameplate of that fan. By simply drilling a hole in the stack of that fan and inserting an air probe, you can measure various spots in that fan, middle, a little closer to the edge and at the edge. And you can average all those velocities and determine what CFM that fan is running at. Maybe it should be operating at 5,000, it's only operating at 2,500. That's something you need to investigate further. Again, if you can catch the issue before it becomes a major problem, you're going to save a lot of money down the lane. Now, a data pack is a very powerful tool for analyzing temperature and airflow currents in your oven. When you run a data pack, which all it is an insulated box with a recording device inside and metal probes that are connected to that recording device, you want to run it the same way every time. Ideally, you want to run it, worst case scenario, fully loaded oven. The data pack comes with an air probe you plug into the recording device and various metal probes that you can either use magnetically or clamped on that act as thermocouples that measure the temperature, the surface temperature of that part. So the outputs you get from a data pack are one, a graph, a visual representation of the temperature and air currents in that oven, and a data table, which you'll need to set up prior to sending the data pack through. A little closer inspection of the graph that you'll receive. If we zoom into the entrance of, there's the graph. What you want to do is make sure you label those probes before you put them in so you know exactly where they were on the part, and you can repeat this the next time you do that same measurement. So as we enter the oven, you can see that red air temperature is the first one to go up. It's going to react the quickest. The spike you see there is the part traveling through the air seal, high velocity hot air. Spikes up, goes back down as it enters the vestibule and the initial, whether it's a gel zone or dehydration zone. But as you can see, right from the get-go, there's a large discrepancy between most likely the top 4 probes and the bottom 3 or 4 probes. As we move into the initial cure zone, again, the air temperature spikes, it's going to react the fastest, and the parts continue to grow. But at this point, you can see the blue line indicated here and here, which is the hottest on top, the hottest air temperature, all the way down to the coldest part is about 100-degree difference, delta T. That's a bit much. So you want to start thinking about how can I minimize this gap and bring these parts closer together at these temperatures? Is it a different hang pattern? Is it more additional ductwork, redirecting the ductwork? And then the final cure zone. This is a nice curve, nice flat curve. You don't want to see peaks and valleys, even in the air probe. You want to see fairly level. And as it enters into the cooling zone, these parts finally almost come up to temperature. But as you can see on this graph, it was set up for 3 temperatures. The cure temperature was 365 for 15 minutes. I'm sorry, 356 for 15 minutes. You could see this probe number 8 never reached it. So the first thing you want to do is investigate that probe, where it's located, how it's hung. Is there some way you can improve that time, or do you have to do other things such as turn the temperature up to meet the specifications? Again, this is something you should do periodically, monthly, just to stay on top of things. You can catch small errors if you compare curve to curve. You can catch these problems before they become big issues and you just ran a whole batch of scrap for a whole shift. Well, in conclusion, just to highlight a few points, understanding your needs for the oven, what is really required for your oven and your product. Choosing the proper location can save you money and energy and efficiency over the life of the oven. And again, I can't stress enough how important maintenance is in a final cure oven. Reduce the amount of dirt in the oven, constantly clean it, and your part's going to come out much better if you don't. So I appreciate your time, and if there are any questions, glad to answer them.
Thanks so much, Brian. We have a few minutes to open it up for questions. Attendees, reminder to please use the Q&A panel in your chat. And as a reminder, the webinar is being recorded and when complete will be made available to you via email from Products Finishing. First question we have is, have you ever seen a batch oven that is both gas-powered convection and IR? Is it possible?
Oh yes, of course it's possible. If you have certain areas in that part that are heavier or thicker and you want to make sure that you can focus, there's the same spot every time, and you put those IR emitters in those areas, that'll greatly help that part come up to temperature quickly. So yeah, I don't see any issues with that.
How much energy does elevating the oven save versus a floor-mounted oven?
Okay, sure. That's a fairly simple calculation, because what you need to do is calculate the amount of air leaving that oven. So I don't know, for say example, if we have just a typical size 5x3 part, and we add some area for the slot, so that's 18 square foot. Say you have 2 openings, that's 30 square foot of opening, and roughly it should be 50 feet a minute exiting the oven. And you take that by the specific heat of air times the delta T of the air, so 70 degrees roughly on the outside, and let's say it's a 350, 400 degree oven. That will give you the amount of BTUs that you're losing per hour out of that oven. Now, if you extrapolate that over a month, over a year, it can be a very large number. It's not uncommon to see 650,000 BTU an hour pouring out the end of the opening. And very quickly, you can calculate your payback for elevating that oven.
Okay, we have a question about, is this the same concept about UV cure ovens? They might be talking about the IR.
No, yeah, UV is a totally different technology, yes.
Okay, how do you recommend to illuminate a hot oven greater than 500 degrees? And also, what sensors do you recommend to detect fallen parts on a conveyor oven?
I guess I don't understand how to illuminate a hot oven. I'm not quite sure I understand how that. I mean, you could preheat the parts using IR to reduce that, not knowing what the part temperature needs to be. You can try preheating it. Maybe you can try to re-question that a little bit. I'll try to come back to it. But fallen parts, there's a couple different ways to test for that. Some of our customers actually use tripwires, physical tripwires that are connected to a limit switch. So if a part hits that tripwire or drags on it, it'll trip a sensor and alert an alarm in the oven. Another way to do it is just through a photo eye. You place various photo eyes through the oven, either lengthwise or perpendicular to travel. So if a part falls or is being dragged through the oven, it's going to drag across that photo eye and do the same thing, alert that there's a fallen part and that has been tripped.
Okay, we have a question about experience with high VOCs, for example, ECAP and powder coating. Is there an air turn rate related to exhausting VOCs?
Well, per NFPA, there is an air turn. I'm sorry, I don't know off the top of my head, but if you have a lot of VOCs in your system, you're most likely looking at an RTO to remove those VOCs at a much greater rate. But I can look at that offline and try to get you a more accurate answer on that. But NFPA would be the one you'd go to.
This question is about the internal air velocity circulating inside the oven. Which is the optimum velocity?
It depends on your part. Well, inside, let's start with the ductwork. Inside your ductwork, we design for roughly 2,500 feet per minute. That keeps the static pressure at a manageable range. If you're going any faster than that, it adds static pressure to your fan and makes you increase the horsepower. At an air seal, it can be anywhere from 4,000 to 6,000 CFM, pushing that air back in. In the actual oven proper, again, roughly 2,500 feet per minute at the discharge of the nozzle is what we shoot for. But you also have to take into account, if you have very heavy parts, you can get away with faster velocities. You have very light parts, you got to be careful you're not blowing those parts off the racks. So there's a couple of different things to consider.
Okay. I think we got some clarification here on the illuminating the oven. They're talking about basically the oven being dark inside, and they tried illuminating the oven with lamps, but it melted them. So I think that's that question is
sure
concerning.
Yeah, in the past we have used just standard filament bulbs, but when you're getting that hot, yes, you'll run into problems. I mean, the other option is not the greatest, but dock door swinging lights, especially with LED lights these days, are much brighter. Installing additional doors so you can put additional swing and dock lights in the oven, depending on what you're looking for. If you're just looking for general, sticking your nose in there and seeing if you can see the parts, that might be enough. But on all our doors, we put dock lights in there.
Have you seen byproducts of cure VOCs accumulate in a cure oven and cause defects on the parts? What's the max percentage of VOCs as a good rule of thumb for powders to minimize buildup? Are there other methods to reduce buildup?
For powders, I mean, there's a lot of different powders out there, but for powders, VOCs typically is not an issue that we've seen. If you have a specific paint that you want to send me, I can take a look at that and see, dig a little deeper. But that's the VOC issues that we normally see are in E-coat ovens, not powder, or even in liquid solvent-borne cure ovens.
Okay. You talked about the oven zones. Could you give more details about the powder oven?
Sure, yeah, I'll try. So the powder ovens are typically segregated into two zones. So the gel or heat up zone, where you're trying to heat up the part slowly with low velocity air. You can use hot air, but it's got to be a lower velocity. That's where IR comes into play, where you're not using any velocity whatsoever, and you're able to gel out the powder paint. So then you move into the second zone, where you introduce higher velocity air to get a better heat transfer in the dwell zone of the cure oven. And those operate at different temperatures. I hope that answered your question.
What is the best method to clean an oven? I was asking if dry ice blasting.
Mm-hmm. Yeah. I've seen that used on conveyor rails. with some success. Cleaning off those rails and any support structure in there. I do know some customers that do use that. Some customers go as far, mostly in the automotive, where they have a washdown oven where the oven is completely welded throughout, so the water can't leak into the oven panels, and they'll go in with pressure washers occasionally and clean the whole oven down. But if you stay on top of your maintenance and periodically do it, having doors in the ductwork can be very helpful. So you can stick a vacuum in the duct every 10, 15 feet and vacuum that out. Can be very beneficial.
Okay. We have a question about space constraints and inability to elevate the ovens. So they're wondering if there are other suggestions that you might have.
Well, yeah, I mean, if you can always put it outside if that is an option. You can elevate it on top of the factory roof, as I had mentioned. But at some point, you need to find a location to do that. If you can't elevate it, again, trying to use infrared as best as you can to reduce the length needed. Infrared is much more efficient at heating the product if your product will accept that type of technology. My rule of thumb that I use is infrared is roughly for every 1 or 2 minutes of infrared is equal to 5 to 7, 8 minutes of convection.
Okay. How many oven turns is correct for hybrid powders?
Well, we design our ovens more on delta T in the oven. So reducing the delta T makes you a more efficient oven. So typically on powders, we're looking at anywhere from 40 to 45 degrees of delta T, which is the differential temperature from the air returning back to the heater box to the temperature of the fan leaving the ductwork. That's how we design our systems.
Would an IR gel oven greatly affect the climate in the E-room if attempting to gel primer powder before applying your top coat?
You will get some radiant heat out of the openings of the IR oven for sure. So the longer vestibules you can put in there will reduce that. I mean, you typically have an exhaust fan in that, so convection heat I'm not too worried about. It's more just the radiant heat coming off of the part and the IR burners that you have to. So if you can do an L-shaped or a U-shaped oven, that would be the best.
Okay. Got one more question, it looks like. Oh, okay. Letting some more sneak in here. Do you have any insights on low bake problems at the ovens? At my company, we've talked about the conditions of the compressed air, but now we're stuck at this matter.
Yeah, I'm not sure I understand the question with compressed air.
Okay, I'll take that one off.
I apologize.
Or see if
yeah, for
sure.
sure.
Clarify. How do you estimate the acceptable air velocity for parts to avoid falling?
That's a good question, and it's really based on experience and how you design your hooks. We work with the end user and sometimes their hook manufacturer to ensure that if they have very light parts, that they're clamping their parts so we can hit them with higher pressure. But for example, if their parts are flat sheets and they're just sails, so if you hit it with any sort of velocity, it's going to start swinging. So we'll design our ductwork more of a down blast above that part. Heavier parts are easy. You can use a lot of velocity. But it really takes a few conversations with the end user and how they're going to design our hooks of how we're going to, how much velocity we can accept on that part. Again, we can direct the air out the side of the ductwork so it slows it down somewhat. So it's more of a rolling heat than it is a direct blast of heat.
Okay. How do I increase the capacity of an old oven?
You turn up the heat. No. Yeah, the simplest way is you just turn the heat up. But when you got to the point, all the systems we put in, we designed it for so many pounds an hour. And after week 1, they've already put in more pounds an hour in there. So they slowly crank up that temperature. And at a certain point, you just can't do it anymore. So one of the ideas that I touched on is putting in prop fans in the oven, just recirculating more air. Everybody always says it's time at temperature, but it's also air circulation. If you can circulate more air in that oven, you're going to get a much better transfer efficiency. Additionally, again, going back to the IR ovens, if you can put even a small heater bank in there prior to the oven, if the application allows it or admits it, that'll preheat your parts going into the oven. The final way to do it is just add on conveyor length to the oven if that's possible. A lot of times we'll remove the back end of the oven or the side of the oven and add an extra 1 or 2 passes. At that point, we would probably add another heater box on to account for the additional load.
Okay, we'll take one more. From the air makeup unit, what is the percentage air humidity that you recommend?
From the air makeup unit.
Yeah.
I'm not sure if you're talking about the recirculation fan in the heater box or from the air inlet by the burner. Typically, we don't see any issues with moisture in an oven causing defects. I mean, there's systems all over the country and world where you're constantly adding humidity, if that is the question. And that's not something we see as a problem very often. I mean, if you have more specific questions, I'd love to answer that offline.
Okay.
Try to get to the root of that question.
And it looks like we've got a clarification on the compressed air question. We use compressed air at the painting pistols, and basically the air is pressurized, affects the painting baking process. I wonder if we could solve this problem by manipulating the oven conditions.
Well, if you're talking about the compressed air in the powder booth, it could be that you've got too much moisture in your compressed air line. I'm just trying to postulate what you could be talking about. If you have too much moisture that's in your powder paint, yes, that is a problem. And I don't think the oven's going to be able to solve that. You need to solve that at the root of the problem by putting a desiccant air dryer on your compressed air line.
Well, it sounds like that's kind of the end of our questions, and sounds like there's a few things that might be clarified best.
Great. I'd love to follow up. Sure.
Awesome. Well, thank you so much, Brian. Appreciate your time today and this presentation. It's been great. I'd like to also thank our attendees for taking the time to join us today. We appreciate you being here and hope you'll join us again for the next products finishing webinar. For more information, visit pfonline.com/webinars. Have a great day, everybody.